KURINJI Senior Secondary School, CBSE, Namakkal.
Successful result producing school in state every year.
Administered by the Board of Directors with over 35 years of experience in the teaching field.
Special attention on art, craft, music, dance, silambam, yoga, skating and karate.
Focus on Hindi Sabha and Spell Bee Olympiad exams.
Smart class for effective and innovative learning and well-furnished library.
Solitary importance on sports and games in state and national level.
WhatsApp facilities to know activities of students and school inside the campus.
NEET, JEE, IIT coaching experts from Rajasthan and Andhra Pradesh along with our effective teachers.
Admission registration for classes LKG to +2.
KURINJI Educational Institution, Kavetipatti, Namakkal. Admission in progress. CBSE, KG to 12, contact 9025895176. Metric 6 to 12, contact 9344567484. For online admission, log on to www.kurinjischoolnkl.in.
In continuation to the last class, this is the second class from Rotational Motion chapter. So in our previous class, we discussed what is a rigid body and what kind of motion can a rigid body have. Okay, there itself we discussed what is meant by pure translational motion, and the example of pure translational motion, that is what a block coming down from an inclined plane in rectangle shape, right? So a rectangular shaped block coming down from an inclined plane. Okay, right. So afterwards we also discussed about that different bodies are in different motion, sometimes the combination also, okay. So what about the motion of a fan? That is what generally, what is axis of rotation and what is rotational motion, and what about the potter's wheel, and then what about the oscillating table fan, and what about the spinning top. Here itself we discussed what is the axis of rotation, right, and how a body is going to rotate. So basically how a body is going to get rotational motion, and what is rotational motion, and if you throw a body in two different situations, that is a rigid body, in what situation it is in pure translational, and in what situation it is the combination of translational and rotation, right? So these are all we discussed in our previous class. So there itself we learned what is a rigid body, and what is meant by the situation of pure translational motion, and what is meant by the situation of combination of translational and rotational motion, and what is meant by axis of rotation, and what is rotational motion, what is the difference between circular motion and rotational motion, right? So these are all we discussed. Okay, now in this class our concentration is center of mass. Okay, right. You know very well, even in previous class also I discussed to you, when we talk about body, so it may be either small or big. For example, a car and a train. So when compared to the car, the train is bigger. But when we need to talk about the displacement, velocity, acceleration, momentum, force acting on the body, so when we talk about all these things belongs to one particular body, whether it is car or train, how to consider the body? You know, if you see the car, the mass is very less. If you see the train, the mass is very big. So how can we consider? Right? That's why not only the car, not only the train, even if you take living beings, for example human, what is the structure of the human? Similarly, what about the buffalo, and what about the snake, and what about that glowworm, right? So that's why, because of these different shapes of distribution of mass, whether it is living or non-living, when we are going to discuss about either displacement or velocity or acceleration, whatever it may be the quantity, there it is better to consider the imaginary point. It is better to consider a point. It is better to consider a point where the total mass of an object concentrated. That point is said to be center of mass. That point is said to be center of mass. Okay, right. So basically, what is the center of mass means is an imaginary point where the total mass of an object supposed to concentrate. Center of mass is an imaginary point where the total mass of an object supposed to concentrate. For example, you know that in classroom the students are playing with the exam pad. They will keep their forefinger or central finger at the middle of the exam pad and they will make it to rotate. How it is possible? They concentrated the forefinger, the ending of the forefinger, the sharpness of the finger at the center of the exam pad so that it can easily rotate. Okay. So not only for exam pad, any object, whether it is living or non-living. So whenever there is a mass, for that mass we can imagine an imaginary point, that is what where the total mass of an object supposed to concentrate, and with that you can balance the object. With that you can balance the mass of the object. That's what I want to say. That's what I want to say. Okay, right. So here itself, before going to enter into the discussion, I will repeat once again. Center of mass is an imaginary point where the total mass of an object supposed to concentrate, right? And at the same time I want to say one more point. Suppose if you take the bangle, so what the ladies are going to wear to their hands. If you took the bangle as an example, so its the center of mass is at the center of the bangle. So at the center of the bangle there is no mass. Suppose if you take a 1 rupee coin, right, 1 rupee coin which is which has a uniform distribution of mass. If you take 1 rupee coin, its center of mass is exactly at its center, that you cannot touch. That you, if it has some thickness, you can't touch the center of mass of the 1 rupee coin. So that's why center of mass is an imaginary point, right? Sometimes it is within the body, sometimes it is outside the body, right? So that's why sometimes you can touch, sometimes you cannot touch. And if you see the geometric, if you see the regular bodies, for example triangle, rectangle, right, and square, and if you see like this regular bodies, the geometric center coincides with center of mass, no doubt. But in case of irregular bodies, we are not sure, right? So irregular means which is not regular, okay, right. So in this class our discussion is to calculate the position of center of mass. Our discussion is in this class to calculate the position of center of mass. Okay, right. See here, for two particle system, so there are only two particles. Just imagine, one is M1, another one is M2, right? When there is M1 and M2, right, so it has its own center, that will be different. But we are going to calculate the position of center of mass of these two particles, right? So it is M1, it is M2, and we imagine one coordinate system, that is what M1 is x1 distance from, that is what, origin, and M2 is x2 distance from origin almost, right? So that is what here. And where is the center of mass here? How to find the position of center of mass? Mathematically, because determination of position is very important, which is required to determine the velocity, which is first which is required to determine the displacement, then it is what, velocity, afterwards it is what, acceleration, then you can go for force, momentum, etc., right? So that's why when I want to know, when I am going to know what is the position of center of mass of these two particles, that is what m1 and m2, right? It is x1 and it is x2. And okay, for example, the distance of center of mass of these two particles is at one point, that is what C, and the distance of the center of mass of these two particles is x from this is what origin, is the distance some origin, that is what x. Okay, right. Now if you concentrate here, so what about the position of center of mass? See here, the center of mass of the system is that point C, which is at a distance x from O, when x is given by x is equal to m1 x1 plus m2 x2 divided by m1 plus m2, right? It is what equation number 1. Here, what is the m1? Mass of one particle. What is m2? Mass of another particle. What is x1? Distance of first particle from origin, and x2 is the distance of second particle, that is what m2 from origin, divided by m1 plus m2, right? It is what equation number 1. Okay, next. So I told you what is m1 and what is m2 and what is x1 and what is x2. Okay, right. So here x, so whatever it may be, x here, that is what indicating the position. X can be regarded as the mass weighted mean. X can be recorded as the mass weighted mean of x1 and x2, right? So this x1 and this x2, this x1 and x2 both are same, right? So don't think that just how we have different types of English letters, right? First type, second type, like that only, right? But anyhow, it is also x, it is also x, right? No difference, right? Next, if two particles have the same mass, for example, in this situation, if two particles, whatever the two particles, that is what m1 and m2, having same mass, then what will happen? So then you can write like this now, that is what m1 is equal to m2 is equal to m. m1 is equal to m2 is equal to m. So when you are writing these values here, what will happen? X is equal to m into x1 plus m into x2 divided by m plus m. That is what x1 plus x2 by 2. x1 plus x2 by 2. So it is what x. When two particles having same mass, that is what x is equal to x1 plus x2 by 2. See the difference. So here we assume that the two particles having different mass. Here we assume that the two particles having same mass. When they are having same mass, x is equal to x1 plus x2 by 2. So for two particles of equal mass, the center of mass lies exactly midway between them. So based on this I am saying, right? I am not saying on my own. Based on this I am saying. Okay, right. Next, for two particles of equal mass, the center of mass lies exactly midway between them, right? Okay, so if we have n particles of masses, just the discussion, the concept he is going to extend, right? If we have n particles, small n is the number of particles, right? So if we have n number of particles of masses m1, m2, m3 and so on up to mn respectively along a straight line taken as the x-axis. So like this, m1, m2, m3, m4, m5, like that, along x-axis, okay, along a straight line taken as the x-axis, then by definition, what is the position of center of mass of the system of particles? This is only, no. You know, when this is the expression for two particle system, this is the expression for n particle system. What is wrong with it, right? We need not to think bigger. That's it. So this is the expression for n particle system when the particles are distributed along a straight line taken as the x-axis. Okay, right. So is the position of center of mass. That is what? Okay. This one you can write like this, no, mathematically, just by using a summation symbol, right? That is what sigma I is equal to 1 to n mi xi. It is what sigma I is equal to 1 to n mi, right? That is. So here what about this x1, x2, x3 and dash 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 xn? These are the distances of the particles from the origin, right? X is also measured, that is what indicating the position of center of mass, also measured from the same origin, okay, right? And one more very interesting thing is here, this is what we can write as a capital M, no? See, sigma I is equal to 1 to n mi means what will happen? This is the mass of sum of the mass of all the particles. Then this one you can replace with capital M, which is the total mass of the system. Total mass of the system. Okay, right. So suppose here, okay, it is what 2 particles along x-axis. Here it is what n particles along x-axis, right? Suppose you have 3 particles. Suppose for example, we have 3 particles not lying in a straight line. Not lying in a straight line. We may define x and y axis in the plane in which the particles lie and represent the position of the 3 particles by the coordinates like x1, y1, x2, y2 and x3, y3. Generally plane means xy plane, no? So x coordinate and y coordinate because of 3 particles x1, y1, x2, y2 and x3, y3, right? Okay. And what about the mass of the 3 particles? As usual, m1, m2 and m3. Then what about the center of mass of the system of these 3 particles? And how can we locate the coordinates of center of mass? Okay, see here like this. X is equal to m1 x1 plus m2 x2 plus m3 x3 divided by m1 plus m2 plus m3. This is what x coordinate of center of mass, and then it is what m1 y1 plus m2 y2 plus m3 y3 divided by m1 plus m2 plus m3. This is what y coordinate of center of mass. Here also you just consider one imagination, that is what one assumption, right? Otherwise one of the thing, that is what you just if you just think of masses are equal, the masses are equal means the same thing will become like this. This is what x is equal to x1 plus x2 plus x3 by 3 and y is equal to y1 plus y2 plus y3 by 3. Okay, right. So for 3 particles of equal mass, the center of mass coincides with the centroid of the triangle formed by the particles. I will repeat once again. For 3 particles of equal mass, the center of mass, COM means center of mass, the center of mass coincides with the centroid of the triangle formed by the particles, formed by the 3 particles. Okay, right. Now see here, the results of these equations, that is what here these 2, that is what equation 3 and 4, equation 3. So the result of these 2 equations, that is what giving, right? So that is what generalized to a system of n particles. The same thing you can extend to n number of particles now. When you are going to extend to the n number of particles, generally what will happen? X is equal to m1 x1 plus m2 x2 plus dash 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 mn xn divided by m1 plus m2 plus m3 dash dash mn. Similarly, y is equal to m1 y1 plus m2 y2 plus dash 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 and so on up to mn yn, and then in the denominator m1 plus m2 plus dash dash up to mn, right? So here it is what in case of either x and y, right? The same thing you can write like this. This is what x is equal to sigma, just by using summation symbol we are writing sigma mi xi by m, right? And sigma mi yi by m, and sigma, that is what zi by m. Okay, so here these 3 things, that is what these 2, whatever these 2, here the particles are in plane, no? The particles, the masses are in plane, right? So when we generalized this one to a system of n particles, and then not necessarily lying in a plane but distributed in space. That is what space means. Z coordinate will come into the picture. So when the particles are not in the plane, distributed in a space, then center of mass such a system. So there, what about the coordinates of center of mass? Means like this, just what I told you just now. So here, this one I am assuming as equation 5, this one I am assuming as equation 6, this one I am assuming as equation 7. Okay, right. So from these three equations, so whatever the equations we have, here as usual, in place of sigma mi, directly we put as total mass, that is what, capital M, right? Okay, and this is what the position, right? The same thing, it is what individually we are writing the x coordinate, y coordinate and z coordinate. Okay, right. Afterwards, suppose if you want to write a single equation by representing all these things, that also possible. How can we write? See here, the equations 5, 6, 7 can be combined into one equation. That is what the equation, see here, Ri is equal to, this is what, xi into I cap plus yi into j cap plus zi into k cap. That is what you can write. Okay. Next, see this one. Capital R is equal to, this is what, position vector, ith particle, right? Ith particle, and this is the vector form, that is R is equal. Generally there should be bar, no? So what is the notation of the vector? So you have to write one letter and top of that you have to put one bar. Otherwise, thick English letter you have to write. So this is what giving vector form x into I cap plus y into j cap plus z into k cap, where this also you can write by using summation. That is what, R bar is equal to sigma I is equal to 1 to n, obviously, mi ri by capital M. So this is the right handed, the sum on the right hand side is a vector sum because it is a position vector. I is equal to 1 to n. Okay, right. So the origin of, suppose for example, see here, here I have written clearly, that is what, see here ma. Suppose in case of a rigid body, right? In case of rigid body, okay, before this I want to say some other information. That is what, this one is over, no? Just we have written these all the things in one vector form, that is either this one or this one, right? So this is for n number of particles, it is for 3 and it is for n number of particles. Okay, right. Here suppose if we took, right, origin of our coordinate system, origin of the frame of the reference as a center of mass. Generally, you know what is the coordinate system, no? X axis, y axis, z axis. Suppose if you take origin of the coordinate system as a center of mass, then we need to write sigma mi ri. Sigma mi ri is equal to 0. Okay. So till now in this class we focused on particles. So in first case we focused on 2 particles, and then that we extended for n number of particles distributing along x axis. Then we came to discuss, that is what, 3 particles in a plane and 3 particles in space, right? Then it will be the situation. And when equal mass is there, here also when equal mass is there, what happened? So till now we discussed about the particles. Now the question is, for example, if you see a rigid body, that is what, like a meter stick or flywheel, so anything, whatever. Suppose if you take the meter stick, so how many number of particles are there? So there are more number of particles. And one more thing is, the distance between the particles is very less, almost negligible. So in such type of situation, it is difficult to apply this process what we discussed, right? So this process is difficult what we discussed. So that's why we are going to use calculus method. So integration, we are going to use calculus method, right? So by using calculus method, how can we write the coordinates of center of mass? How can we write the coordinates of center of mass? See here, see this. This is what x is equal to sigma delta mi xi divided by sigma delta mi and y coordinate and z coordinate. The same thing you can extend like this. It is what integration dm, and it is what integration x dm, and it is y dm, and it is z dm, right? So here the coordinates of center of mass are x is equal to, y is equal to, and z is equal to. Here also you can write that is vector expression, r bar is equal. This is the general expression for all the things. R bar is equal to 1 by m into integration r dm. Okay, right. So if you choose center of mass as the origin of our coordinate system, that's I already told you, but here also we are applying the same thing. If we choose the center of mass as the origin of our coordinate system, then r is equal to 0. R is equal to 0. That is what integration r dm is equal to 0. Then you can also write that is what integration, that is what is meant by this. If you choose the center of mass as the origin of coordinate system means x is equal to 0, y is equal to 0, z is equal to 0. Then what about these all the things? Will become equal to 0. Will become equal to 0, right? So in this manner you can find the position of center of mass in calculus method. So if you will find x coordinate of center of mass and y coordinate and z coordinate of center of mass, then that is only the position of center of mass. That is what x comma y comma z. Okay, so this is in case of continuous bodies. This is in case of continuous bodies, right? So that, for example, if you take the bodies of like water, rings, discs, okay, spheres, even thick rods of either circular shape or rectangular shape, for all such bodies we have to realize that for every element dm, that is what small amount of mass at a point x, y, z, so you can always, one can always take an element of the same mass at the point minus x comma minus y comma minus z. So it is what symmetry, right? The point of reflection symmetry, right? So whatever the integrals we are seeing, when the position of center of mass is at origin, so that will be equal to 0 like this. Integration x dm, integration y dm, integration zcm is equal to 0. I already told you in the starting of this class. In case of regular bodies, center of mass coincides with geometric center. Center of mass coincides with geometric center. For example, you are taking one regular body which is in rectangle shape like this. Then where is the center of mass? Here, no. Suppose if you take like this coordinate system, then what will happen? So it is 0 comma 0 comma 0, no, right? So that's why in case of regular bodies, center of mass coincides with geometric center. Okay, right. So in this class we discussed, our concentration, and we discussed about the position of center of mass. Okay, right. So in case of two particle system, you know very well, for example, when you go for park, Namakkal, park, you know there is what a seesaw, right? So one child is sitting on one side, another child is sitting on another side, and they used to move, right? That is what first this child will go down, and this child will go up. Next this child will go down, and this child will come up. So it is what seesaw. So there two children are sitting, are separated by certain distance. No, that is the best example of two particle system. So at the time, where is the position of center of mass? Suppose if the child is having same mass, then what about the position of center of mass? So when the children is having same mass, either particles or children's, then the center of mass is exactly at the middle of both the children. Okay. Similarly, if we extend the discussion to n number of particles, what will happen, right? And by using summation symbol, how can we write? Suppose in case of n number of particles also, if n number of particles having same mass, equal mass, then what will happen, right? Similarly, so suppose the particles are not distributing along x, along y, along z. The particles are in space. Then what about the position of center of mass? So the position of center of mass means first you have to find the x coordinate, y coordinate and z coordinate of center of mass. That is only our interest. Okay. So like this you can find out. Okay. After completion of that, the same thing you can also generalize by using the vector notation. That is what, okay, we used the result, that is what capital R, that is like resultant of all the things, right? Okay. After completion of that, one of some other situation, that is what continuous bodies, for example meter stick, okay, and flywheel. So here in case of continuous bodies, it is difficult to apply the process what we learned, because there are huge number of particles, right? That's why we consider, that is what calculus method. So we use integration. The summation is replaced by integration here, right? So that is what we discussed in this class. So in our next class, we are going to discuss some example problems based on this information what we already discussed in previous class and this class. After completion of that, we will go to discuss motion of center of mass. Okay, right. Thank you.